Hello everyone, I'm Sajin Park. I will present our work on how we efficiently scale DNN training by bursting too many GPUs only when necessary. This work is done with my colleagues at MIT, Josh, Songyeon, Mohammad, and Adam. One of the trends is the complexity of DNN model is increasing over and over. But the improvement on GPU processing power has not kept up with the demand for compute. So we are left with no other choice but increasing the training cluster size. For example, Facebook and Google has been using hundreds of GPUs or TPUs to train their models. But there is still a question on how we should scale DNN training. The conventional approach to scaling was increasing the batch size with the cluster. In other words, weak scaling. With weak scaling, each GPU runs as many samples as possible in each iteration. When given another GPU, that GPU also runs the same amount of samples in each iteration. So we double the batch size. So with the more GPUs, we are increasing the batch size more and more. This approach has some nice properties. Weak scaling can almost linearly increase the throughput because it keeps the GPU utilization pretty high and amortizes the communication cost. But this approach stops working at some point because once the batch size becomes too large, the statistical efficiency of each sample drops. So training with more GPUs doesn't reduce the time to reach the desired model accuracies. In this example, training with 256 GPUs doesn't really give any benefit over using 128 GPUs. We just saw that naively scaling batch sizes with more GPUs won't scale to very large cluster. So to scale beyond that, we can divide the large batch of samples into fine grains and distribute them to more GPUs. Then each GPU has less work, so it can finish each iteration more quickly, which we call strong scaling. If we combine weak scaling and strong scaling, we can achieve better speed up, especially with the hundreds of GPUs. However, even this alternative approach is not 100% efficient and gives diminishing speed up eventually. The reason is each GPU often does not have enough work, which leads to GPU underutilization. Basically, we have to waste our GPU resources to achieve the best possible speedup. Fortunately, we spotted an opportunity to mitigate such GPU underutilization problem. One of the reasons of GPU underutilization during this strong scaling is parts of DNN layers are not strongly scalable. When we divide 128 samples and distribute it to 64 GPUs, some layers get almost 64 times faster, but some layers harder to get any faster. So what we can do here is bursting the number of GPUs only when we can get benefit and shrink the number of GPUs for the layers that doesn't scale well. When you shrink the number of GPUs, some of the GPUs will become idle. To reclaim the unused cycles, we should have some background jobs that can fill in. For a large GPU cluster, there must be multiple users and many different kinds of tests. Especially, there should be two kinds of training tests. Large ones that require distributed training over hundreds of GPUs. But also, we must have some small jobs that can fit in a single GPU and can tolerate slowdown. So in theory, we should be able to reclaim the unused cycles from distributed large-scale training by running small and not time-critical tasks on background. By exploiting the two opportunities I just mentioned, we can enable high speed up for time-critical large tasks while achieving good cluster efficiency. In summary, we first exploit burst parallelism, where we adjust the scaling of each layer to reduce the waste of GPU resources. And secondly, we reclaim the idling GPUs by multiplexing with a local background job. To demonstrate our solution, we built a distributed training system called DeepPool. DeepPool takes a PyTorch-like model description, dataset, and a cost parameter on how much inefficiency it should allow. Then a burst parallel training planner decides the scaling of each layer to maximize the speedup, but within the inefficiency limit given by the user. We run a runtime instance on each GPU in the cluster, and the runtime manages multiplexing foreground and background job in that GPU. Burst parallel training planner determines the level of strong scaling of each DNN layers for training. It takes the optimal global batch size and the number of available GPUs as input. And its search algorithm has two components, but let me show you the first component, dynamic programming for a chain of layers. For a chain of layers, planner determines the right number of GPUs for each layer. Here, the key criteria for a scaling decision is efficiency. As metric, we use the aggregate active GPU time for each iteration, which we call GPU second. It's like man hour or watt hour. And specifically, we compare GPU second when scaled and not scaled. For example, for the layers that scales pretty linearly, the GPU second will not amplify much when strongly scaled. Then those layers are strongly scaled to all available GPUs. On the other hand, for layers that don't scale well, GPU second will linearly increase. So we assign fewer GPUs to them. The limit of allowed GPU second amplification is a user's preference. So this seems to be a very simple process, but we need a dynamic programming because of communication overhead, specifically when we change the scaling. So there are activations, and so when you change the scaling, there are activations and backpropagations across GPUs. So we must consider those communication overhead, and this overhead depends on the previous layer's configuration. So we need the dynamic programming. Another big part of DeepPool is ensuring quality of service for the time-critical foreground job while multiplexing with the background. For multiplexing, DeepPool relies on two NVIDIA GPU features, CUDA Stream and CUDA Graph. CUDA allows users to set priorities to streams, so we run foreground jobs with a high priority stream and run background jobs with a low priority stream. However, using stream priorities alone did a very poor job on ensuring the quality of service for high priority tasks. The reason is there are device queues shared by all stream priorities. So if the shared queue is filled with the low priority kernels, then scheduler cannot find the high priority kernels. Also, the block scheduler used by NVIDIA GPUs is not preemptive. So once low priority kernel is scheduled, high priority tasks must wait until they are finished. So to mitigate those problems, we implemented multiple mechanisms. For example, DeepPool's admission control ensures low queue depth for the shared device queues. And we use small batch sizes for background tasks to reduce the impact of a non-preemptive block scheduler. To evaluate the performance of DeepPool, we trained 3 popular image classification models with the DGX A100 box, which has 8 GPUs connected by very fast NV switch. And we mainly answered 3 questions listed here. The first question is, can we improve training throughput of each GPU while strong scaling a foreground job? To answer this, we benchmarked 3 models with the 4 different settings. First, DP is our baseline, which runs vanilla data parallelism. Second, BP runs a foreground task with a burst parallelism without any background task. Third, BP plus collocation collocates a low priority background task while running a burst parallel foreground job. To make it easy to understand the throughput of each GPU, both foreground and background trains the same model. And lastly, as a reference, we run a background job only, which suggests the potential maximum band throughput of the cluster. For VGG and wide resonant workloads, BP plus collocation almost doubles the cluster-wide training throughput. And our multiplexing mechanism worked pretty well and confined the foreground's quality of service degradation under 18%. However, for inception, burst parallel train schedule falls back to the standard data parallel strong scaling because the inception has pretty even scalability across layers. In the last slide, we saw a particular operating point of a DeepPool for each model. In fact, DeepPool can run in multiple different operating points with a different inefficiency tolerance and collocation aggressiveness. And to illustrate the trade-off of cluster inefficiency versus foreground speedup, we now use a different baseline, which statically partitions the GPUs in a cluster into 2 groups, a set of GPUs for a foreground job and another set of GPUs for background job. When you compare the multiple operating points of DeepPool with the baseline, DeepPool can achieve higher foreground speedups for the same total cluster throughput level. Now let's zoom into how DeepPool's individual multiplexing techniques enable low interference collocation. Before collocating, we applied CUDA graph, which improved the throughput of the foreground. When you collocate a background task, the throughput of foreground task drops to almost 0. Even with CUDA stream priority, because of the shared queues and non-preemptive scheduler, foreground hardly gets to run. But once we introduce launch pacing so that the depth of shared queue are kept low, foreground regained about half of the throughput. With additional admission control mechanisms which blocks the foreground task if the foreground is expected to suffer, the foreground regains 76% of the throughput. Finally, by using smaller batch sizes for background jobs, foreground throughput improves to 87% of the original throughput. To conclude the talk, I presented two techniques to improve the efficiency of extremely large-scale DNA training: burst parallel training and GPU multiplexing with the minimal interference. But DeepPool also has some limitations. Our work only explored strong scaling on the sample dimension and parallel computational graph. Also, our runtime currently doesn't support distributed background jobs.